Right? Can we wrap it up in a week or so?
Wrap what up?
How about this? How about a week from? How about on Tuesday? Let's get an update from each team. Where you are. Like I said, there are 2 projects, so let's try to finish it in 1 or 2 weeks. The first project, then we'll move into the second one. Okay. So I don't want to rush you. We have time, but I think this is week number 4. Next week will be week number 5. Pretty soon will be half semester over. Okay. So we'll have 9 teams, 9 projects. Maybe the leaders take 1 or 2 minutes next class on Tuesday. Give us an update. Let me give us a sense of where you are. How many days do you need to finish it? Okay, so maybe we'll finish it the week after next week, something like that. But let's put it on the map. Okay? And also related to that, I'm giving you an assignment for the writing. The writing assignment could be related. But this will be this is an individual assignment. This is on the Blackboard. I sent it to Tucker. Did you put it? Not yet. Okay. So, but sometime today. So let me talk about this a little bit. This is probably something different, something you haven't seen before. We cover all these inventions, inventors, and I'd like you each one of you to write an essay on it. Right? Of all the stories, or maybe the story you discover yourself, which one impressed you the most? Why? Could you tell a story about it? Could you interest somebody maybe non-technical? This is why I'm interested in electrical engineering. This is what I get my inspiration. This is what's so motivating for me. More of a personal statement, as opposed to copy something from the web and put it in the. I want to hear your voice, your motivation. Why are you here and not in some other colleges or some other department? You. Yeah. What is it about you? So that's I give you a rough guideline. I don't want to pin you down on anything specific. So basically do research on a major invention, idea, or person in the history of electrical engineering. We went over Faraday, we went over Ørsted, we went over so many people, so many astounding discoveries that changes the world as we live today. Yeah? We get to have some inspiration from those, right? Right? We're flesh and blood human beings. We get motivated by these great people, great genius, and their ideas and their inventions. So I want use this maybe as a way to help you rediscover your passion for learning. After all these courses in science, in mathematics, in chemistry, in physics, where the stuff is crammed down on you. I want you to rediscover, hey, I study engineering because of this. I study engineering because I one day make a discovery, however small, a discovery. Something hasn't been done before. So this is the general motivation behind it. Going forward, I like to use this maybe as a starting point to write a script. Based on your essay, maybe write a script, produce a 3-minute video by the end of the semester. Tell your story. Tell your story to the world. Okay? And that's an individual effort. Yeah? And team-wise, you have 9 teams. So every team, everyone on your team write something, right? And maybe the team together can decide we want to produce a team video related to our project. So that's up to you. That's up to the team. But this is an individual one. I want to see from everyone. I want to know about you. I want to see what you did. I want to see what interests you. And to some extent, I like to advise you. on your career path. Like I said, my career is more or less behind me. Yours is in front. There are things I can share with you, to avoid some traps, to build a bright future for each one of you. So this is not just some abstract speculation. This is real. This is something I hope you discover about yourself, right? And I want to know about each one of you, although you have 49 students. So to tell the story in your own voice, I can see it. I can see it from a mile away, whether or not something is yours. It's something authentic. It doesn't have to be perfect English. Don't worry about grammar. Just tell the story as it comes to you. Tell what you think. Tell what you want to do in your career, in your life. Yeah. So that's the writing assignment. Right? So maybe after I see what you got, maybe I'll advise you to write a script. Maybe we'll produce a video. We don't have to, but that could be in the future. But let's start with this writing assignment. Okay? I'll give you 2 weeks. I think that's reasonable. Yeah? Any questions? Yeah? If you want, you can talk to me after the class. I have office hours. Yeah? So maybe let's move on to the website. I want to go back to this chart, degree map. Right? Where in this semester you're taking electronic 1. I think most of you, electronic 1, circuit lab, circuit 2, and signal and systems. I also want to let's see here, remind you what this course is cover and overlap with this class. For example, the circuit 1 you already took. Right? You use the computer simulation. You use the RL circuit. I want to use that as a jumping point, and this is one that you are currently taking. You're doing the AC circuit, magnetic coupled circuit, that transformers, frequency response, resonance, right? Transfer function, Fourier transforms. So that course is going to cover a lot of nuts and bolts. So instead of repeating that here, I'm going to show you how you use it for a practical use, to give it life, to show why such tools are important, and also who invented this, what problem they were facing, right? And also electronics. In electronics, you also see frequency response. So you see this everywhere. Body plot. What frequency response? Body plot. So here we are in circuit system. We covered it, but we covered it in the context of engineering problem, solving engineering problem in communication, in controls. And in our case, we'll start with controls. So that's. Do we want to get started on?
It's recording.
It's already? Okay, great. Fantastic. Right. So this is what we started last time. Frequency response as applied to controls. Right? So I give you a scenario, and I give you a historical background, so you know where it comes from. When you know where it comes from, it makes it a bit easier to digest, to follow the train of thought. I suppose something foreign, something that you don't know where it comes from. So frequency response is a simple concept. You have a system, you have input, you have output. You send a sinusoid to the input, and you measure the output, also a sinusoid. And you, in steady state, you measure the changes in magnitude, the changes in phase angle. Together, that is called frequency response. Of course, these are different frequencies. So by nature, frequency response is a graph. The axis, the horizontal axis is frequency. The vertical axis is either the magnitude and angle. And together, they are called Bode plot. That's simple, right? That's not hard to understand. How do we use it, however, takes time. So that's my main goal, is to show you how this is used. Because you're going to see this again and again in communication, in controls. And like I said, in the past, most people, even at the senior level, do not really have a good handle on, maybe they have a good handle on Bode plot, but how do we use Bode plot to design a good control system or good communication system? I believe that we shouldn't push that to the senior year, although we have a lot of senior students here. I'm glad you're here. But I hope even some of students are taking the control system today, this semester. Definitely, control system is, of course, after the senior course, right? So in the future, control system will have this course as a prerequisite. So by the time you get to control system, you already know how to use frequency response to solve problems. Right? So you ask those seniors why they're taking this class, why they're still finding it useful. Right? So that's frequency response in the short definition, the short statement. The nuts and bolts are, I think some of you already did it in your project. You told me that you have a circuit, you derive transfer function. From transfer function, you set S equal to J omega, then you graph it. It's called Bode plot, right? So some of you already done it. Even if you haven't, it's not the end of the world. It's not the end of the world. It can be done. It can be done rather straightforward. Bode is known for making it simple for us. You can use straight line approximation, quickly sketch a Bode plot, a frequency response of a system. And from the sketch, you already know what the system does. Powerful. Simple and powerful. That's why Bode was awarded a large military contract during the Second World War. He outcompeted against the MIT professors who is knee-deep in mathematics. And his solution, although a little bit different, maybe a little bit less superior, but his solution is so simple, so intuitive, the military adopted his method. That's Bode plot. That's why we're still talking about it today. So Bode made it easy for us. We should be thankful, not be afraid of it, not be scared of it. There's no reason for doing that. So that's frequency response, and I went over this last time. Low pass, band pass, high pass. Very intuitive, in terms of magnitude. In terms of the magnitude response, and also what does it do for us? What can we do with frequency response? And I gave you this example last time. I'm going to use it again today. So keep it in mind. I want to refresh your memory. This is a motor control, right? And this is the coil. I sub A, armature current. Right? So that's the electronic part. That's the electrical part. The power side. That's the mechanical side. You're using motor to drive something, to drive a load. In factory, for moving parts. And be careful. The load will have a force coming back to your system. We call it load disturbance. And the load is not easy to handle. then the torque, the acceleration, get to a velocity, get to position after 2 integrators. So 2 integrators, and the torque become a final motor position. Devin.
I'm sure this might be a stupid question, but
No.
I take a picture?
Of course.
Okay,
Of course. Just don't have me in it. For seniors, for 440, isn't this one of the problem you're solving? Could be. Maybe. Maybe you haven't seen it yet. So I'm giving you something that the senior students see it later in the semester. This is what I mean by putting the problem in front of you. This is the problem. Every motion control engineer faces this problem. So that brings all the attention, all the focus. What do I need to know to solve this problem? To solve it better than anybody else. Let me ask you a question. I give you a simplified model. I said this model can be explained from a frequency response. How? How? We know given the transfer function, make S equal j omega, and then you can graph it. Right? That's how you go from transfer function to frequency response. But it seems that I suggested the reverse. I suggested that this is the system, this is the input, there's the output. I can go by definition of frequency response and find this transfer function. How do I do that? Inject a known sinusoid into the voltage here. And then what? Yeah. Either compare the output here or take the velocity from here. I actually did this 30 years ago in the lab when I was a TA. There was a DC motor, and I put a signal generator, put the output of signal generator to the voltage input of power amplifier, and I changed the frequency. Then I get a set of points. Then I connect them. Then I get body plot. From body plot, I can get transfer function. Very easy. No physics. We don't have to be a physicist to understand how the motor works. We don't even have to know Newton's law of motion. A lazy method, but nonetheless very effective. Very effective. There's one overhanging question though. You should have observed and you should have asked, but maybe you are not used to it yet. But let me tell you what the question you should have asked. Look at this diagram. How many S do we have in there? How many S? How many terms that have S in the denominator? Two or three? So yeah, these two are obvious. From torque to position. Motion, Newton's motion. You give a force, proportional to acceleration, but from acceleration to velocity is integrator. From velocity to position is another integrator. So these are obvious in motion system on the mechanical side. But what about electrical side? Do we have some dynamic there? Do we have energy storage? We do. That's a coil. That coil in the motor. Derek, you showed us the coil last time, right? That's energy storage device. That got to have S in there, at least one. See? Engineering is not difficult. It's intuitive. Unless it's taught by a mathematician. So we have three energy storage, or three dynamic components in here. One is the motor. Look at this. You see the transfer function 2.5 over 0.02 to S, 0.02 S plus 1. right? So you have voltage coming in, and you have current going out. That's your coil, no? It's a coil. It's an inductor. We just wrote it differently, but it's a coil, right? So that's the transfer function of a coil. You put the voltage in, you get current out. See? Mathematics is easy if we know what is going on. Right? But the connection is powerful. There are many people who can see the coil, who can touch the coil, hopefully without electricity in it, but not able to see the mathematics, not able to think about it as an inductor, as a AC circuit. So be able to write the transfer function is a knowledge all electrical engineer must have. And this is your circuit. Come on, this is a circuit, right? You have inductor. You have you put the voltage in here. You induce a current, right? So what's the transfer function? What's the transfer function? Yeah, let's call it V of S. Let's call it I of S. The current. Right? So what is the current? What is the transfer function of the output over the input? So the impedance is L times S, right? That's the impedance in frequency domain. Then you avoid the differential equation altogether, right? And the impedance of this is R. So what is this? Right. The voltage drop. That's a loop, right? So the voltage drop. This is IAR, right? That's voltage drop here. The voltage drop here is what? IA times SL, huh? Right? Yes. This is Ohm's law generalized to impedance, right? So now I can write a V of S equals IA S times R of S plus SL. No? Yes? So what's the transfer function? That's it. And if I want to put it in a standard form means this. This is 1 over R. This is 1 plus S L over R. Yeah? Can I put it in that term? That's where you get this. That's how you get this. That's a transfer function. Can you do it? Can you do it yourself?
Yeah.
Probably yes, right? Probably yes. That's your quiz question. That will be in your quiz. That will be in your exam. In some variations. You like that? There's no surprises. This is the engineering skill we are trying to let you have, not some hoops to let you jump through. And everything we do for a purpose. Right? So getting so now we see the transfer function of this, and represent a real physical device. Right? Moreover, I look at this transfer function. I see a time constant. Do you see a time constant? I see a time constant. And this time constant tells me how fast this inductor is charging. I put the voltage, say 1 volt in there. How many seconds does it take for the inductor to be fully charged? From the transfer function, I can see that it takes about 0.08 second, 80 milliseconds to charge this inductor. Do you know how I can tell? Do you know that?
What's the 80 inside that power amplifier?
No, it had nothing to do with that. It had everything to do with this. So this is another thing that I'm not going to go into details because these are nuts and bolts that you will learn from other courses. But I can tell you this: if I have a transfer function like this, first order transfer function, okay? I can show you mathematically, although I won't do it here. If I give a step input, my output is going to be like this. And based on the transfer function, I know the steady state value of this is k. And the amount of time it takes is 4 times tau. Again, I can show you mathematically. It's very easy. Okay? But that's not the point. It's not that's not the point of how do we prove it. I just want to show you with simple mathematics manipulation. I can show that the given transfer function like this, I can quickly tell you what the system is doing. The system is going to be charged to a constant value of k, and it's going to take 4 times tau. This is tau is a time constant, and it takes 4 times the time constant to be fully charged. Actually, to be charged 98%, to be precise. But engineering-wise, it's fully charged. So I look at this transfer function. I know this inductor has a convergence time of 80 milliseconds. That's important, right? Because there's a timing requirement for me to move something from point A to point B. I need to know how fast I can move things, and this is the critical number, right? But it doesn't show up in here. This number doesn't show up in here. So I ask you why. Why is it I have 3 energy storage devices here, and I end up with second order transfer function, and here I have time constant of 20 milliseconds, and doesn't show up in here. It turned out if you do frequency response, right, that your response is dominated by the mechanical side. Mechanical side is much slower than the electrical side. The motor is much faster than the movement. So therefore, for the most part, most time we can get away with ignoring the dynamics of the electrical side. How do we ignore it? How do we ignore it? We treat this duration, 80 milliseconds, like nothing, because our movement, when we move the stuff, we move about in the range of about 1 second. 1 second, we can move from point A to point B. That's pretty good. That's generally the acceptable industrial response time. Compared to 1 second, 1 second is 1,000 milliseconds. 80 milliseconds is nothing. Okay? So therefore, engineering, not physicists. Physicists will go crazy. Can you ignore that? Come on. We build a $1 billion accelerator just to find out what's going on, and you ignore it. Right? So that's a very different mentality. But engineering, we try to get away with what we can get away with. Yeah.
Is there a way besides the Bodhi plot that comes up with that transfer function?
There is one. And for that, you have to ask Dr. Li Didong. Project he did for a local firm manufacturing automobile motorcycle pistons. And this is the Simulink model he established for that system, and this is the transfer function. And in 440, I showed that in 440 you learn a technique called frequency response based design. Right? The central concept of that is say this is your a closed loop bandwidth requirement. Your design specification will tell you how fast the closed loop bandwidth has to be, and this is your open loop response. Where it is? This is your open loop response. GP times GC. GP is given. GC is what you design. So this is the design principle that we're going to follow, right? And this is later on in this semester, I'm going to teach you how to convert your solution from analog to digital. But that's relatively straightforward. It's this part that requires some attention. Okay, so I'm going to this is what we did last time. So we also talk about the body, yeah, understanding where he's coming from. What Nyquist did. We're going to use the Nyquist method. Nyquist method is based on frequency response. So I'm going to show you how that is done. And this is the way we covered last time. And this is by Nyquist his own words, that he derived all this mathematics just to find a stability condition that agree with experimental findings. So he was a great engineer that able to use the mathematics to its full extent and explain what up to that point is unexplainable, and that Nyquist plot. Nyquist plot is going to be discussed in detail in 440, but I'm going to give you a taste of what it's like. Nyquist published paper in 1932, 5 years after the invention of negative feedback. He was compelled to do it because nobody could explain why negative feedback go unstable sometimes. And this became a seminal paper. This was collected in the book in 2001, 25 seminal papers in control theory. I would even go further. I think this is the most important paper in control theory. Okay, nothing compared to this. But again, that's my own opinion, and it's extremely intuitive. So this is amplifier. This is the black amplifier, and when you hook up the output to the input, great result happen. Negative feedback. You have a constant gain. The gain doesn't vary anymore, and you have linearity. Two most important characteristics you can want from a circuit, from amplifier circuit. By the way, amplifier is a topic of today's discussion. I just saw in the news some people at MIT invented this huge amplifier that amplifying 5G signals. Okay, you know about 5G, right? From 4G to 5G, but the problem with 5G is the short distance. You need a lot of stations, so being able to amplify signal become a urgent technical need, and somebody at MIT invented a 5G amplifier that amplifies signal by 20 dB. 20 dB. What's 20 dB? What is 20 dB in layman's term? Huh? 20 dB. We take a log, we get 20 dB. We use dB to characterize the gain. But what's before? What is the number before we take 20 dB? Before we take the log? I tell you, but it's too simple. 1 is 0 dB. Good try. That is also very important, 0 dB, we'll show you. 100 is 40 dB. now you know, right? So what's 20 dB? Half of 40 dB on the logarithm scale, but in the original number, 20 dB corresponds to the amplification of 10 times. Again, these are nuts and bolts. You are going to see it over and over again in circuit, in electronics. Right? But that's what we are seeing here. An amplifier, huge gain, maybe 100 dB. Yeah. Maybe 120, 150 dB, huge gain, right? But not linear, but not steady enough. So in 1927, Harold Black invented negative feedback. So he solved the problem of linearity. He solved the problem of gain variations, but he introduces a dangerous side effect. What is dangerous about it? And this dangerous side effect showed itself up everywhere in mechanical system, in chemical, in aerospace, everywhere. That the minute you close the loop, you introduce the hidden danger. The loop can blow up in your face. You can have many good characteristics if it works, but if it doesn't, you can burn it easily. You can burn your chip. You can induce explosion, out of control, vibration in mechanical systems. And Nyquist, I cannot emphasize this enough. Nyquist was the only one who cracked the problem. There are many other pretenders. Many other mathematicians come up with fancy formulas. The Nyquist was the guy who solved the problem. And it's very easy. He said, just send a bunch of sinusoid through the amplifier and obtain the frequency response. This is one example. This is the original signal. And this is output signal. What's the difference in terms of magnitude and phase angle? What's the difference? What's the difference? The magnitude is smaller, less than 1. Less than 1, so therefore less than 0 dB. Okay? 20 log 1 is 0. Anything less than 1, you get negative 10 dB, negative 20 dB, so you are in the negative territory in dB. So this reflects a particular frequency where instead of amplifying, this amplifier is attenuating your input, right? It's not amplifying at all, right? So that's number one phenomena we observe. What's the second one? What about the phase angle? Is it ahead or is it behind? Is it ahead or is it lagging? Lagging. The phase angle of the output is lagging. You can clearly see the shift or peak. The peak moves forward backward, right? So that's lagging. So this and this that difference is how much lag in time, but not in angles. You have to divide it by the angles. Not divide by the angle. You divide it by the period and multiply by 180 degrees. Then you find the phase angle lagging. Right? So this is okay if the amplifier for this frequency is attenuating it. It has a huge phase lag. But as long as the amplitude is attenuating, it's not going to be unstable. What Nyquist and his colleague observed is when amplifier is amplifying, then you have a huge phase lag. That's what causes instability. And that's experimental findings that he talks about. If you're amplifying and it's lagging, then you close the loop. No, don't do that. Your amplifier is going to ring. It's not going to work. So that's experimental discovery. We don't need any mathematics to see it, to see the pattern. But what we are lacking is the mathematical understanding of what causes that. And more importantly, how do we modify the circuit so it doesn't do that? Okay? So that's Nyquist. That's his theory. And he tells us from the frequency response, based on the frequency response of this amplifier, without feedback, based on the frequency response of the amplifier, he can tell you whether or not when you close the loop it will be stable or not. And based on his condition, we can go and modify the circuit in amplifier so it becomes stable if it's unstable. And moreover, even if it's stable, we can still measure how stable it is. How close is it being unstable? And so that's the contribution of Nyquist, and it's all illustrated in this particular diagram. And this diagram is so intuitive. You just cut the feedback loop and you send a bunch of sinusoid into your loop, and you collect the output. If at any frequency the amplification is larger than 1 and the phase lag is 180 degrees or more, you are sure you have an unstable closed loop amplifier. Okay, so that's Nyquist's stability condition in a nutshell. Cut it, look at this open loop, send the sinusoidal to it, and if at any frequency amplification is larger than 1, and the phase shift is larger than 180 degrees, cut it, change it. Right? And that's unheard of. Right? So this diagram makes no sense to you at this point, but it will very soon. So this diagram represents the complex plane. This is complex. This is real. This is imaginary. Okay, and this is the graph of your frequency response. It gets the magnitude and get the angle. So for every frequency, it's a point on this graph. So this is not body plot anymore. Body plot is magnitude versus frequency, angle versus frequency. Here, this is real, this is imaginary. Okay? But it doesn't stop you from plotting from plotting this and this together. At each frequency, it's a point. At each frequency, it's a point on the complex plane. Thank you. Yeah. Okay. So what does the we say we have a transfer function. We have a transfer function of 206 s over s plus 3. Right? And we we make S equal j omega, and this is our frequency response. Right? It's a complex function. So this thing has a magnitude and this has an angle. For every frequency, it's a complex number, right? Yes? So how does it look like if I graph this frequency response for omega from 0 to infinity? What does it look like? And that's what is being graphed. Let me tell you, if you pay attention, it's not difficult. If you don't pay attention and you read books on it, it's going to take you weeks. Okay, on average, maybe you're smart, days. Okay? But on average, weeks. Yeah, this is why when I teach this stuff, people don't read books because they make a mess. And for most textbooks on this, they made a mess out of this. Right? I'm going to show you in a simple, concise, easy way how to graph this. It's easy. Right? Now, when omega is 0, you have a constant. About 70, and it doesn't matter, right? But what I want to see is when omega from very small, right, and going to very large, right? When omega is very small, when omega is much less than 1, this is what? This is very large. This is correspond to 206 j omega, and this is very small, so you can ignore that. Times 3, right? And what is the angle of this? What is the angle of this? You have j. This is a pure imaginary number, right? 90 degrees. This is 90 degrees. Right? If you graph it. This is 0 degree, 90 degrees, then minus 90 degrees. Right? And if you have point alpha plus j beta, if alpha is 0, this is here, right? If beta is positive, so that's 90 degrees if it's j omega. But if it's in the denominator, then this is minus 3 omega 203. 206 j, right? You multiply both sides by j. So now you have a negative number. Now instead of here, you're here. So that's negative 90 degrees. You follow me? You follow me? If you don't follow me in the back row, plan for 2 hours of reading tonight to understand this. Okay? So initially, omega is small. This is like a 90 degrees, minus 90 degrees. And the magnitude is almost infinite, because when this goes to 0, this is infinite, right? So that's what you're seeing here. That this is 90 degrees, way down there. Right? And that's your initial position. That's when omega is approximately equal to 0. As omega increases, the magnitude will decrease, right? You go back to this. As omega increases, your denominator becomes larger and larger. Eventually, it becomes 0. When omega goes to infinity, let's come to this point. The magnitude equals 0. So now you have two extremes. Initially, you were way down there at minus 90. Eh? And when omega becomes very large, you are here. It doesn't matter what the angle is. you are excuse me. You're at the origin. Yeah.
Why is the real number considered negative then? Why are both of them in?
Well, if you graph this, Why this? If alpha and beta are both positive, you are here, right? I'm assuming this. So if alpha is 0, you are here, J beta. If beta is negative, you are here. So that's what I got here. This is equal to that, and this is J, and this is your beta. Your beta is negative number, so you're down here. And when omega is very small, you're way down there. You follow me? This is not difficult. Nyquist plot is not difficult. But the book, I have not seen one book get it right. No, get it right in terms of make it easy to understand. It's a mess. Okay? So that's the general shape. That this will start with almost negative J infinity. Okay? And gradually it becomes 0. This is omega much less than 1. This is omega much larger than 1. So you have two extremes. Okay? And I would graph like this. It comes down from here, and it approaches the origin from 180 degrees. So this is minus 90, this is 90, right? This is minus 180. Okay? Why it approaches origin from negative 90, from negative 180? Because when omega become very, very large, this is approximately equal to 206 J omega square, right? You can ignore 3 when omega become very large. So this is J omega square. Now J omega square, these are 2 J omegas in the denominator. Each one give you minus 90 degrees. So 2 of them together give you negative 180, which means it's negative 1 omega square. That's negative 180. That's a negative number. That negative number is the negative 180. So this is negative 180, right? But this is somebody else's plot. For us, for our transfer function, it's going to approach the origin from the negative 180. Okay? That's it. That's our Nyquist plot. That's our frequency plot. That's not a Bode plot, because Bode is plotting versus frequency. This is plotting real versus imaginary. So we're looking at the rho and zeta. That's how we plot it.
Is there a significance from when it crosses the real plane?
Very significant. Yes. That's what I'm going to talk about next. Okay. So what did Nyquist say? Well, Nyquist said that on this plot, on this complex plane, and you graph this, right? And on this complex plane, this is like a graph like this, right? The stability of the feedback amplifier depends on this fact. This is negative 0 point. And that's red dots here. This is the critical point. As long as your graph doesn't get anywhere near this, you're stable. What is this point anyway? Magnitude equals 1. Rho is magnitude. Rho equals 1. The system becomes unstable when you have this condition. And Nyquist proved it mathematically, and this corresponds to negative 1, 0 point. Negative 1, this is a complex point, right? The real part is 0. The imaginary part is the real part is negative 1. The imaginary part is 0, and that's this representation. Okay? Alpha equals minus 1, beta equals 0, and this defines this point on the frequency plot, and if your frequency response plot doesn't get anywhere close to this, you're stable. If it's going to the origin inside of this, you're stable. If your frequency response plot, even though you do not graph it accurately, as long as that this circle, this represent uncertainty, doesn't overlap this point, you're stable. All you need is to graph it. Then you know. And if you're not happy with it, if you're not happy with this plot, you have a choice. In the amplifier design, you can redesign your amplifier. In the amplifier design, you have an amplifier, and that's your. If this graph is not good, redesign this. That's what Nyquist theory tells you. How do you redesign this so that it becomes good? Right? In our case, we cannot redesign the plant in the controls case, but we can redesign the controller. In our case, we have a GP and we have a GC. GP is given. GC is to be designed in control system. So all we need is to understand how do we design GC so that GC GP, in this case G equals GC GP, give us a good plot. Okay? So what we are graphing is this. What we are graphing is GP. And we're seeing this, which is not bad. Yeah? But in order for us to control the system well, so GP is 206, S plus 3. Yeah? But for control system, our task is to make Y goes to R. We force the output to follow the command. That's a different problem from Nyquist, from Bodhi. Bodhi and Nyquist are concerned with stability of the amplifier. Amplifier itself is doing fine. All we need is to make it stable. Here, the problem is different. The problem is to make output follow the input. How do we do that? How do we make the output follow the input? Well, if you're practicing control engineering for 20, 30 years, your immediate solution is this. That's your solution. This is your GP, and this is called PI controller. Huh? This goes way all the back to James Watt. The James Watt invented a flyball governor, give you a KP, a proportional controller. But proportional controller doesn't work, or at least doesn't work well if you have a load disturbance coming in. And engineers found out that we always had load disturbance, be it friction, be it something introduced into the loop by the load. We're using motor to drive a load, right? The load comes back to us with a disturbance, and our control has to overcome it. And that disturbance is coming in this form. And this is normally a constant disturbance. But in order to overcome this constant disturbance, you must use the integral control. Everyone knows that in the control industry. Although I'm not going to go into detail, I'll let Professor Li Dong to tell you in controls class. But I'm just take my word for it, and this has been working for over 100 years, this controller. PID or PI, mostly PI. Right? And this introduced a twist. Because if you combine this with 206 over S plus 3, you got a problem. What problem do we have? Well, now our controller, now our G equals GCGP. So this transfer function is this S KPS plus Ki. So now our GC and GP all together, you have KPS plus Ki 206. You have S, and you have S, and you have S plus 3. That's our new G, right? New open loop transfer function, and GCGP. So this is a GC times GP. Right? Instead of looking like this, now it's different. Instead of 1S, you have 2S. So initially, when omega is very small, instead of 90 degrees or minus 90 degrees, you get minus 90 degrees, minus 180 degrees. So you could come in like this and shape like this. And this is that negative 0 point. And that's bad. It could do this, or it could do the other. The other possibility is it does this. They still end up at the origin, but they come into the origin from negative 180 and get very close to minus 1 point. And this is why with the PI solution, with the PI controller, this thing can easily go unstable.
So when it touches that, does it have to touch that point exactly, or when it?
It depends on KPKI. It could come from above or it could come from below.
Yeah, I understand. But I'm saying, you're saying that this point is like really bad, and I'm thinking, is it bad when you get near it, or when you? Yeah. I got it. Yeah. So for this, to understand the whole thing, we need to plot both the negative frequency and positive frequency, and we will see that it's the encirclement. So instead of this is just the real part, omega from 0 to infinity. That's a really good question. To answer that question, I need to be a little more elaborate on Nyquist plot. What did Nyquist say? Nyquist actually is the following. Nyquist says this, that this is S. On the S plane, I define the contour, a half contour. This is the right half plane. You forced me to do this, okay? I didn't plan to, but your question can only be answered if I give you the whole picture. Okay? The Nyquist, so what's S plane? S equals sigma plus j omega. Okay? So the real part is sigma. The imaginary part is the j omega. Okay? So Nyquist defined the contour. This is the part 1, this is the part 2, this is part 3. Okay? Part 1 is j omega from 0 to infinity, what we used to have. Okay? Part 2 is, this is infinite radius. This is infinity, right? Including the entire right half plane. Okay? And part 3 is omega from negative infinity to 0. So mirror image of this. Okay? So Nyquist said, this is called the Nyquist contour. Nyquist contour. This is named after Nyquist. He said, let us do this. Let's do the clockwise. Okay? And let's watch what G of S does. Okay? G of S does this. G of S is the function. Mathematically, it's called mapping. Or engineering-wise, it's called a curve. You have a closed contour here. You have a closed contour here. Okay? And this is that infamous -1, 0 point. So if my original plot of the G of L looked like this, this is my part 1. So if omega goes from here to here, okay, that part 1 of the plot is this, what I just draw here. Part 2, when s equals infinity, G of S stays here. Part 3, when omega from negative infinity to infinity, that's a mirror image of this. Okay? Then you have a singularity at the origin. You take a small contour here, and then that's a part 4 now. Then this thing takes this turn. Take a right-hand turn. Here is the right-hand turn. Like you drive a car, you take a right-hand turn. Here you take a right-hand turn. That's what Nyquist mathematically proved. Now, if this contour doesn't include -1 point, you are safe. Okay? So if your original plant, this is your original plant. If you make controller equal KP equals 1, you're safe. You're okay. This thing doesn't go unstable. However, it doesn't reject disturbance. To reject disturbance, you have to add the integral in there. But when you add integral there, now you are doing this. Say, for example, this is your part 1, and part 2, the mirror image would be this. Then you take a right-hand turn. Then you encircle this point, -1 point. Then it becomes unstable. Right? The details, I'm not going to go into it. But this is going to take a right-hand turn. And it's going to encircle -1 point. That's what makes it unstable. It doesn't matter whether you are crossing it or not. It's a matter of if you encircle it. Both of these do not encircle it. If you push the gain large, if you enlarge, say multiply by 100, this point will go over to this side, and that becomes unstable. So Nyquist plot tells you how much room do you have in gain variations. So immediately it tells you the limitations, how high your feedback gain can be. Right? And this tells you how much uncertainty you can tolerate in your gain and phase angles. Right? So what I'm coming back to this, what I'm showing you is you can play safe. Your system will be perfectly stable, but it doesn't perform as well as you want it to. But when you push the performance, when you add integral control in here, integral control will help the system to reach to make Y follow R perfectly in the steady state. This will happen in steady state, but the cost of that is adding an integral control, and the cost of that is making the Nyquist plot very complicated. You can still stabilize it by manipulating the gains, or maybe by adding a lead-lag compensator, by adding a compensation network into it. You can still manipulate it, but your stability region is very limited. And Nyquist plot shows you how to do that, how to graph it, and how to use this understanding to redesign your controller, to determine KP, KI, or to determine whether or not you need a feedback compensation network. So I go into this with a little more depth than I planned, but I hope I didn't lose you completely. The mathematical intricacy, you will learn that in 440. Dr. Li Dong will be the perfect person to learn that from. But what I show you here is what Nyquist means to us. What this tells us in design. Somebody have a question?
Oh yeah, is this mentioned in the regeneration theory paper?
Yes, yeah. It's a very hard paper to read. I have to warn you. Very hard. Right? So this is what people say after they were introduced to Nyquist. The knowledge of Nyquist changes the control from trial and error to systematic design. So in the past we were just guessing, but now Nyquist gave us a tool to kind of systematically go about doing it. Even if it's a PI control, we can still make it stable. But we have to be very careful. And then you can ask, why is it today that most practicing engineers are still doing trial and error tuning PID? Because most of them don't understand Nyquist. They don't understand the Nyquist because they all took controls considerably. They all took controls, but they never understood it to the extent that they can apply it. And so that's why, if you really understand it, it empowers you. It makes you different. Makes you a shoulder above everyone else. What's going on with this? Okay? So I think our time is up, but I think we get to the point what Nyquist can do for us. So in next lecture, I'm going to give you a little more details about this example. Okay?